Hi, everyone. We're the Ramblin Rex team, and our Capstone project is Modular Impact and Deformation Fan Testing for Tectronic Industries, or TTI. The foundations of our project revolves around developing a batch testing procedure and rig for the impact testing of axial fans. The intent was to be repeatable, precise, and produce quantifiable data that can compare each manufacturing run of fans. However, as the project has progressed and the design has come to fruition, the scope has expanded slightly to a more generalized testing in two specific criteria. In order to improve the current design, we wanted to implement an empirical testing methodology that accommodates brittle and ductile fans. The ductile fans will undergo deformation at progressive loads, and the displacement will be measured. Meanwhile, the brittle fans will undergo an impact test where the energy taken to break the fan blade will be measured. Sizing the mast cart and drop tower height are critical first steps to the design process. In order to estimate impact forces, a set of example impact times for a variety of materials was obtained and applied to find the mass to induce failure in several modes where bending was dominating. In the top right is a plot that summarizes the maximum mass to induce bending failure at half a meter of height. Here is an overview of the system showing the mass drop cart, calibrated mass, live axle fan clamp, rotary indexing table, XY adjustment table, the worm gearbox and motor, and the electrical housing. The rotary toggle and fixture frame holds the live axle toggle clamp, roller bearing, main axle with thrust puck, and the gearbox stepper motor component. This was designed like so to provide a large range of angles to place the fans and achieve orthogonal impact points on the blades while maintaining a stiff base for the main axle.
The cone holding the fan in place from the top is designed to make the fan coaxial and provide additional support, keeping the fan from popping off the mechanism by bouncing. It has been designed to spin freely with the fan, only providing axial forces, and fit every fan type that is available currently by TTI. A large circular disc with a thin sheet of sandpaper adhered is used to provide necessary friction against torque while maintaining a universal fit. The thrust puck is attached to the main axle, which is a simple multi-radius shaft that reduces the risk of bending while simultaneously fitting into the hole in the bottom of the fan and connecting the gearbox shaft. A tapered roller bearing and pillow block were designed to eliminate all loading on the gearbox except for axial torque while still allowing full rotation of the indexing function. The shaft is held in place by a press fit while the bearings retention to the pillow block can be adjusted and required copper shims during prototyping due to the hole saw curve. The NEMA 17 motor and the 17-1 worm gear were chosen to prevent the backdriving of the motor to maintain the repeatability of the test. However, upon obtaining the gearbox motor component, mounting turned out to be difficult as the gear was placed directly in line with one of the bolt holes. Additionally, while the motor is de-energized, the motor can still backdrive slightly and has considerable backlash. It is recommended to replace this gearbox with a zero backlash gearbox. The fan clamp in practice was very effective but could use a few modifications such as securing the washers to the clamp arm and tack welding the bottom nut for ease of use. The XY table performed its job but was not very smooth and requires manually tightening the gibs to prevent backlash from affecting results. The mast cart system is triggered by a solenoid. It is designed so that it can be mounted on different heights as well as have varying calibrated mass, allowing tests to be performed at different amounts of energy. For prototyping purposes, the mast cart was 3D printed and bolted to the linear rail sleeve bearing. It was designed to be a T-beam structure due to superior performance in bending, shear, and compression.
The firing pin was designed to withstand high impact forces and compression between the mast cart and the fan blades while delivering the most force and precision to the fan blades without jacking. The design includes a compression spring that acts as a reset and allows the firing pin to automatically start at a higher point and return to that point after impact, which is nestled between the head of the pin and the plastic spacer to prevent overcompression. Here is a short slow motion video of the impact of the mast cart on the firing pin, which caused the fan blade to snap at the root as expected. The newer, larger grip plate slightly interferes with the fan blades as it breaks, which essentially creates a ramp that causes the firing pin to slide down at an angle. The electrical housing box for the fan indexing is a freestanding box that connects all elements of the circuit while still allowing the operator to move the buttons to any desired location around the fixture. The controls include 3 push buttons which allow for direct user interface and an emergency stop button. The push buttons will, for example, index the forwards one blade, increase variable values, or confirm the selection. This is a simplified wiring diagram that will be included with the project when handed off to the sponsor for troubleshooting and updating purposes. The code was designed to be simple and straightforward to operate and allow for rapid indexing between fan blades. However, during our testing, the gearbox proved to be insufficient tolerances, and the gears allowed for substantial backlash, even when the motor did not turn at all. For this reason, a different one will be recommended for use rather than the one used for prototyping. The deformation test turned out to be highly sensitive to the friction in the sleeve bearing and indicates that the bearing material should be changed. It is also recommended that an indicator flat be designed into the carriage for easier measurement setup. In practice, the flex arm was convenient and did its job very well. Thank you so much for your time, and we will now take questions.